Our next unit is going to be studying gases and the behavior of gases. Interestingly enough, and coincidentally, I'm also working with this as my freshman, and their lecture is actually a highly modified version of your lecture. One of the biggest differences, though, between freshman level gases and junior level gases is we don't focus too much about converting how gases begin at a certain pressure, volume, or temperature and how they change. We're going to go ahead and briefly look at that and jump right into the ideal gas law and then the more applied chemistry with gases. A few reminders when it comes to gases. There are many pressure units, we'll discuss those, but most importantly is the issue of temperature. Celsius is commonly used in a laboratory environment, and it's generally okay to use. 1 degree Celsius is roughly the same size as 1 degree Kelvin. The issue that we have with Celsius in gas laws is that 0 degrees Celsius is a real value and one that can be commonly measured. It's in a freezer. The same thing with negative Celsius. That's a common value. It's not too hard to get to negative degrees Celsius. With our gas formulas, they pose real issues. Most commonly, temperature will be a denominator. If you divide by 0, you literally can't. You get no answer. If you divide by a negative number, another real value for Celsius, you end up with negative pressure or negative volume. That's impossible. This isn't Doctor Who. You're not going to have an infinitely expanding TARDIS box. We have to address that. So whenever we're working with temperature and gases, we must always use the Kelvin value. Kelvin equals your Celsius degrees plus 273. But we'll see this again. So let's begin with some basic characteristics of gases. We study gases before we actually study solids and liquids at the freshman year because they're easier overall. Now, this year we focus on something new. We went ahead and studied liquids and those intermolecular forces. Well, gases don't really have those intermolecular forces, and that makes them easier to study overall because, for the most part, they all behave the same. So, gases, they always expand to fill their container. They're also highly compressible. They're impacted by pressure quite a bit, and they also exert their own pressure. And they also have very, very low densities. And the reason they have low densities is because of their low intermolecular forces and how much they're spread out. And because they're so spread out, they don't really interact with one another, which makes them predictable. We can't have a discussion with gases without talking about pressure. Now, pressure is technically a physics topic. It's force, physics, divided by area. Here, for example, atmospheric pressure is quite literally the weight of an entire column of air that goes all the way to space, pushing down upon you. And atmospheric pressure is a very common thing that we study. Now, we do have a few issues with pressure, and that has to deal with the units. The standard SI is a Pascal. It's a very, very, very small value of pressure, 1 Newton per meter squared. Very, very tiny, actually. And we commonly scale it up, for example, to a bar or simply 100 kilopascals. Bar is often used in meteorological studies and weather studies. There are other units, for example, and the primary reason is because when pressure and gases were studied, numerous scientists were studying them at the same time, and they ended up using their own units. For example, a millimeter of mercury or a torr. This is derived from an actual device that was mimicking a thermometer, a tube full of mercury, but this time it's not closed, it's an open-ended tube full of mercury in a vat. This allowed the atmospheric pressure to push down on the vat and cause the mercury in the tube to go upwards. So this is quite literally the height that the mercury was transitioning up and down inside that tube of glass. So 1 atmosphere pressure is equal to 760 torr, and that is the exact same thing as 760 millimeters of mercury. This we covered in your freshman year. Now, a laboratory device is commonly used as a manometer, although they're falling out of favor these days because of the issue of mercury inside the device. We'll briefly take a look at this here. In this device, this is an analog device, you'd have a closed chamber full of a reaction, a gas being created. It would push upon a tube that's full of mercury. The atmospheric pressure is pushing back down on it. Knowing the atmospheric pressure and knowing the height difference in the mercury, we can calculate what the gas pressure is actually going to be. These days, we don't use manometers too much. We instead have electrical gas pressure sensors. What they have is a bladder, an air bladder, and as gases push on them or the pressure decreases and the bladder pushes back outwards, the voltage that is put it across that bladder changes. If the bladder shrinks, the voltage increases. If the bladder expands outwards, the voltage decreases. The change in voltage tells us what the atmospheric pressure and how the pressure is being modified. Now, let's summarize a few things here from your freshman year in regards to pressure. Normal atmospheric pressure, what we're at right now at sea level, is simply known as standard pressure, 1 atmosphere. That is the same thing as saying 760 torr, which is exactly the same thing as 760 millimeters mercury, and that is also equal to 101.3 kilopascals. All three of these units are commonly used, even though the kilopascal one is really the only official SI unit. Let's briefly review some of the laws that we saw in your freshman year, starting with Boyle's Law. Boyle's Law is the relationship between pressure and volume, and here it's an inverse relationship. Well, that means when one goes up, the other goes down. For example, if pressure is being increased, then that means the volume has to decrease. That's a common example. If I have a balloon and I push upon the balloon, the volume of the balloon is going to shrink. That's Boyle's Law in action. Notice here that it also mentions a constant temperature. The wording of that's important. Whenever you hear the term constant, that means you don't have to worry about what that variable is. So, taking a look at Boyle's Law, adding a little bit more to your freshman year, if we plot the values of pressure against volume, we end up with a curve, and K is merely a constant. So if we simply plot it as pressure to volume, we don't get the right answer, so to speak. That means that if I plot the inverse, volume against 1 over pressure, I end up with a straight line. The concept of trying to plot a straight line is going to be important in a few units when we talk about chemical kinetics, but this is where we come up with the inverse proportion. Another important law is Charles' law, and this is the relationship between volume and temperature. And volume is directly proportional to the temperature. Hot air expands, cold air contracts. We see this pretty often whenever we have changes in the seasons. Most commonly, it's very obvious in wintertime. In wintertime, when the cold air sinks to the floor, it's more dense because it's contracting. So we have a lot of cold air on the floor. All the hot air, when the heater's running, floats up to the ceiling. And if you stand on a chair and you put your hand up on a ceiling at wintertime, you notice it's extremely hot up in the ceiling. This is why fans, whether you realize it or not, have a little switch on them. Rarely do we need to use a switch in a fan during here in South Texas, but that little switch in the fan changes the rotation of the fan. It allows, instead of pushing air downwards, cooling us off that we commonly use, instead it sucks the air upwards and it helps circulate the cold air up into the hot air and pushes the hot air back down along the sides. And this more evens out a room. Believe it or not, your ceiling fan actually has a use during the winter time in distributing the hot and cold air, making the room feel a little bit more comfortable, as long as you hit that switch. Now, how do we know it's automatically a direct proportion? Well, if we plot volume against temperature, we end up with a straight line right off the bat. There were other laws that were discussed in your freshman year. Gay-Lussac's law, for example, which is the relationship between the temperature and pressure, as well as the combined gas law, which includes all of them all together. We're going to include a new law this year, known as Avogadro's law. Avogadro's law is stating that the volume of a gas at a constant temperature, so you can remove temperature, is directly proportional to the number of moles in that gas. Mathematically, it means that volume equals the number of moles. Once again, K being a constant, something there to help fix the formula. So if we take a look at this, we can see that helium, nitrogen, and even methane gas at 1 atmosphere equals 22.4 liters, which is the same thing as 1 mole. So where are we going with all this? Ultimately results in the ideal gas law, the ideal gas equation, which is our primary focus in our junior year. We know that volume is proportional to 1 over P, an inverse proportion. That's Boyle's law. We also know that volume is proportional to temperature, a direct proportion. And we know that volume is proportional to the number of moles. If we combine all these together, then we know that volume is proportional to moles times temperature divided by pressure. This still doesn't get us to what we know as the ideal gas equation. We've had this K pop up every so often. That's merely a constant. In our gas study, that K value is simply going to become the gas constant, R. Due to the sheer number of units that we use for gases, we have a large number of R values, and this is a list here. Arguably, the most important ones that you're going to see for this unit are going to be the R value that involves atmospheres, 0.08206, the R value that involves torr, also a millimeter of mercury, 62.36, but also the R value that involves a kilopascal. Now, remember, a pascal is technically the SI value, but this little unit right here, this meter cube times pascal, that is merely the same thing as saying a liter times a kilopascal. You'll have to forgive my horrible mouse writing on that one. Divided by mole Kelvin, and then we have 8.314. When we first study gases, we don't commonly use the joule or calorie except if we're integrating it with thermochemistry, which we won't immediately. So, if your problem involves atmospheres, you need to use 0.08206. If your problem involves kilopascal or a pascal, you use 8.314. If it involves torr or millimeter of mercury, you use 62.36 as your R value. Coming to the ideal gas equation that we saw in our freshman year, because we know the proportions that volume is equal to, we end up changing proportional to an actual equal sign involving the R value, and thus we get pressure times volume equals the number of moles times the gas constant times temperature. Using this equation, we can go further to places we didn't go in your freshman year. For example, we can now start studying the density of gases with this equation. To get to density, if we divide both sides of the equation by volume and by RT, we end up getting N over V equals P over RT. Why do I want that? Well, if I recall some slightly older information, for example, molar mass. We know that the number of moles of a sample times its molecular mass, its molar mass, is going to tell us how many grams of that sample we have here. If I plug this into my current formula, multiplying both sides by molecular mass, I end up with the next equation. Mass divided by volume equals pressure times molar mass divided by RT. Well, you know why this is important? Because mass divided by volume is density. And all of a sudden, I have a density formula for gases. Thus, the density of any gas equals the mass divided by volume equals the pressure times the molar mass of that gas divided by the R value times temperature. Thus, we can calculate the densities of any gases. Arguably, what's more importantly is not the density of the gases, but identifying what the gas is. We can take that density equation and rearrange it to find the molecular mass, which means all of a sudden, if I know the density of the gas, that's not too hard, it's mass divided by volume. If I know the R value, if I know the temperature and I know the pressure, I can find the molecular mass of a gas, which means I can identify what that gas is. That's why this formula is more important. Coming to an end over here, we talk about gas laws. We'll finish with a relatively simple concept of partial pressures. And this one's nice because it's just addition. Simply put, the total pressure of a chamber, of a sample, of anything that you have is merely the pressures of the individual gases that are present. Why do we focus on such a simple problem, though? Well, A very common method for gathering and calculating and analyzing gases involves a collection that uses water. So let's take a look at that. This is an apparatus that involves gas collection. We usually have to pipe in gases into some kind of inverted graduated cylinder or beaker so we can measure how much gas was collected. Unfortunately, because it involves water, we also have a vapor pressure. We know that all liquids have the ability to release a little bit of gases off of them. So we have to account for what's happening inside that chamber. Let's take a look at this here. This is a relatively basic experiment. I have KClO3, which is potassium chlorate. When you heat it, it releases oxygen. This is an early precursor to rocket fuel. In order to capture the gas, I'm going to pump the oxygen through a sealed tube into an inverted graduated cylinder or beaker. This is filled with water, and as the oxygen bubbles upwards, I get a bubble. And now I can calculate exactly, assuming it's graduated, how much gas I have inside there. Now, the biggest issue we have here is we also know that the water itself is releasing a little bit of gas in the form of water vapor. So, to calculate the amount of gas pressure actually inside this tube, I have to account for the water vapor. Water vapor is going to be based off of the temperature of the water. I can look this up on a large number of tables that are present and merely subtract the vapor pressure of the water from the total pressure inside the chamber, and now I know the pressure of the gas inside. This is where we'll stop this week with a brief review of some freshman level formulas, as well as a little bit of newer information. In the following weeks, we'll go further and talk about the kinetic molecular theory and how far we can go with gases. Before we begin our problems today, let's take a look at some preliminary info from your freshman year when it comes down to gas laws. We are going to be working primarily with a combined gas law, which is a relationship of pressure to volume over temperature. This is how a gas can change to a different pressure, a different volume, and a different temperature. The subscripts, the 1 versus 2, these merely indicate the conditions, 1 being the initial conditions, 2 being the final or ending conditions. They are related to one another. It's merely a matter of identifying the variables and plugging them in. Now, a few other things. If you hear the word constant, that merely means remove the variable. For example, a constant temperature means you don't have to worry about it. Or a constant pressure means you can remove pressure from the equation. You don't actually have to put those values in. In addition to this, we also can't use Celsius, ever. The biggest reason is that 0 degrees Celsius is a real value, and the same thing as negative degrees Celsius can also be measured. These cause major problems given the fact that temperature is a denominator. So we use Kelvin instead, the absolute value scale. Kelvin is pretty easy to convert into an Kelvin. Your Kelvin degrees is going to be equal to whatever your Celsius degrees plus 273. Remember, always use Kelvin. Then we also have to deal with the pressure units. In your freshman year, you were introduced to quite a few pressure units. For example, 1 atmosphere equals 760 torr, which is exactly the same thing as 760 millimeters of mercury, which is also equal to 101.3 kilopascals, the official SI unit. These are our conversion factors, and we'll be using these to make sure that our pressure units match whenever we work with a problem. So the information we must have are the pressure conversions and the Kelvin conversion factor before we can begin and practice the remainder of our combined gas law problems. In your homework this week, we're going to be taking a look at the combined gas law, and I'll be solving problem number 1 and problem number 2. I've set up a large amount of information, for example, the combined gas law and the variables. This is just to help you out. I don't need to see all of this, but this lets me identify what variables I have. In problem number 1, I can read through it and I see I have 800 milliliters at negative 23 degrees Celsius and 300 torr. What would the volume of the gas be at 227 degrees Celsius and 600 torr pressure? So let's plug in the units that we know. Pressure 1 looks like it's going to be 300 torr. Volume 1 is going to be 800 milliliters. And then temperature 1 is minus 23 degrees Celsius. I'm going to go ahead and plug in the Celsius for a moment here, but I know I can't use it. I have to convert it to Kelvin. It's easy enough to do. Remember, it's your degrees Celsius plus your Kelvin. So we add 273 to negative 23, and we end up with 250 Kelvin. For the ending conditions, P2, V2, and T2, I can plug those in. The ending pressure looks like it's 600 torr. Thankfully, these pressure units match, so no conversion will be necessary. Volume 2 is what we're looking for. It's unknown. And T2 is going to be 227 degrees Celsius, and I will convert that to Kelvin by adding 273. Now we have 227 degrees Celsius plus 273 results in 500 Kelvin. All my units match. I can plug in the variables that I have, starting with torr, milliliters will result in a final answer in milliliters, and then I Kelvin already matches. So pressure 1, 300 times volume 1, 800, divided by the initial temperature of 250 Kelvin equals my ending pressure of 600 torr. I don't know my ending volume, but whatever it will be in milliliters, and divided by 500 Kelvin. At this point, however you choose to solve for it will be entirely up to you. I'm going to work my way through and reduce it and then gradually solve for volume 2. On the left-hand side, I have 300 times 800 divided by 250. I'll plug this into my calculator. And the end result is 960 divided by the right-hand side as 600 divided by 500 times V2, which ends up being 1.2 times V2. Divide both sides by 1.2, so 960 divided by 1.2 will get me my final volume of about 800 V2. Remember, milliliters was the units that was used, and so we end up with 800 milliliters as my final answer. In the second problem I'm going to be working with y'all today, problem number 2, I have the same setup. I have my combined gas law and all the variables listed. Once again, I don't need to see this part. I just need to see you plugging in the variables and then solving. Let's take a look at 2. 500 liters of gas at 700 millimeters and 200 degrees Celsius is put into a tank under high pressure. The tank is cooled at 20 degrees Celsius and the pressure is 30 atmospheres. So that's the volume of the gas. Plugging in what we know here, the initial pressure given to me appears to be 700 millimeters of mercury. The initial volume is 500 liters this time. And then, of course, the initial temperature is given to me in Celsius. We know we can't use that. So we'll take the 200 degrees Celsius and convert it to Kelvin by adding 273. This ends up as 473 Kelvin overall. Now my ending conditions. Ending pressure, P2, is 30 atmospheres. That is an issue. Initially, we were given millimeters of mercury, and now we have atmospheres. Volume 2, we don't know. We're asked to solve for it, so it's currently an unknown. Temperature 2 is 20 degrees Celsius. We know we add 273, resulting in 293 degrees Kelvin. Now, addressing the pressure issue. The units must match on both sides. They currently don't. You could convert one into the other. It doesn't matter which way you choose to go. I'm going to convert atmospheres into millimeters of mercury. Now, you could easily do it the other way, and you'll still end up with the same answer. So this is where our pressure conversions come in. 30 atmospheres. We'll set up a dimensional analysis box. We'll cancel atmospheres and convert to millimeters of mercury. According to the conversion factors, 1 atmosphere equals 760 millimeters of mercury. This cancels atmospheres, and I'm left with millimeters of mercury. 30 times 760 equals 22,800 millimeters of mercury. This would be the unit I use when I plug it into the problem because my units must match. Same thing for volume. Volume was given in liters, so we're going to solve for it in liters. Now we can plug in the rest of our variables. We have 700 as pressure 1, volume 1 is 500 liters, and then temperature 1 is 473 Kelvin. This is going to equal the other side. Pressure 2 is 30 atmospheres, but we've converted that, so now it's actually 22,800 millimeters of mercury. Volume, still in liters, but we don't know what it is. We'll solve for V2. Divided by the ending temperature of 293 Kelvin. Plug that in. And now we solve. Essentially, we reduce both sides and solve for V2. So on the left-hand side, we have 700 times 500 divided by 473. Ends up at about 739.96 equals 22,800 divided by 293 times V2. Reducing that down, we end up with 77.82 times V2, and then we can solve for V2. Divide both sides by 77.82, and it turns out that volume 2 is equal to around 9.5 liters as our final answer. And there we go.